Okay, this is Brad Vogel with Ontotext. I'd like to welcome everyone to Not All Graph Databases Are Created Equally. During the next hour, Atanas Kiryakov, CEO and Executive Director of Ontotext, will be answering questions related to graph databases and RDF triple stores from you, the audience, and our host, Senior Vice President Tony Agresta. At this time, I'd like to thank all of you for joining us today and turn the session over to Tony.
Thanks, Brad, and thanks everybody for attending. Not all graph databases are created equally. I'm Tony Agresta. I manage Ontotext USA. Today, we're fortunate enough to have the founder and CEO of Ontotext, Atanas Kiryakov, presenting on graph databases, but he'll also talk about other semantic technology. The webinar is being recorded, and we will send to everyone who's registered a copy of that recording. Everybody's on mute, but you can certainly submit questions at any time using chat. We're going to try and address the questions as they come in, but if for some reason we don't get to them right away, we'll respond to you via email. Feel free to send in both business-related questions and technical questions. So let's get started. Allow me to introduce our speaker today. Atanas Kiryakov is the CEO and the founder of Ontotext. He started the company in 2000 as an R&D lab within the Surma Group, which is one of the top 3 software businesses in Bulgaria. Atanas served as the product manager of the GravityBe database, which is formerly known as OWL-IM, until 2010. And he's a leading expert in semantic databases. He's authored multiple publications, including featured chapters of the Handbook of Semantic Web Technologies. His detailed accounts of semantic search, information retrieval, and storing the semantic web repositories are still widely read today. Mr. Kiryakov obtained his Master's of Science degree in Computer Science from the Sofia University in Bulgaria in 1995, and his thesis was on knowledge representation. His research interests include reasoning, semantic databases, information retrieval, text mining, and linked data management. Atanas, thanks for taking the time to join us today.
Thank you for inviting me and introducing me, Tony.
We have a number of different types of people on the line today: developers, architects, managers, business managers, users. Some of them are very familiar with graph databases, and some of them just have a little bit of experience. What we thought we'd do today is talk about a number of different topics. First, we'll start off with an overview of graph databases and transition into triple stores, some of the advantages and the design choices that developers make. We want to speak a little bit about inferencing and reasoning, the best practices, and kind of what to avoid when you're doing inferencing. We'll talk specifically about a couple of features in triple stores that are important for users. One is called OWL Same As optimization, and the other is full-text search and connections to NoSQL databases. And then we'll transition into enterprise resilience, scalability, talk a little bit about text mining, and then we'll conclude with success stories. So please go ahead and send questions in as they come up. Atanas, why don't you start off by telling us a little bit about Ontotext?
Yeah, I started Ontotext back in year 2000, and it's essentially a company that builds data management and content management products on top of semantic technology, and semantic technology in all of its aspects, right, all the way from triple stores and reasoning to text mining. Now we are 70 people all together. We are headquartered in Sofia, but we have sales presence in London as well as on the East Coast in the US, in Washington and Boston. Like for the first few years of the company up until 2008, when we got some VC support, we focused in more core R&D that allowed us to develop technology and methods that are substantially ahead of the market. And in the last few years, we've been focusing more on finding the best applications and the best shape in which we can deliver these products to the market. So we've been successful in getting such clients like BBC, AstraZeneca, Department of Defense, and others. So we managed to prove that we can build reliable systems and we can deliver efficiently to a wide range of different customers. and that's quite a challenge when you're sitting on top of quite substantial R&D in the field, like both in terms of research, if you want co-research in reasoning and product development. So we have invested ever since year 2000 more than 400 person-years, quite substantial effort to cover all the aspects of semantic technology and put in one box content enrichment, data management, and a database engine. Yeah, the last thing to mention on this row is since the very beginning we are committed to open standards and to open technology. We are the biggest contributors to such efforts like Gate and Sesame, which are the biggest, some of the biggest open source projects in their fields. And the Graph database and the entire stack is heavily reliant on standards like RDF, RDFS, OWL, Sparkle.
We'll have a chance to get into some detailed case studies at the end if time allows, but prior to that, can you give us just a couple of thumbnail sketches on some of the clients that you have today?
Yeah, plenty of our clients are in the, generally speaking, the content delivery sector, all the way from media like BBC to scientific publishers like Oxford University Press, John Wiley & Sons, and others. To financial media like Euromoney and some other great customers that we are not allowed to talk about yet. We also have telecoms, a quite substantial presence and adoption within the life sciences and healthcare sector, with leading pharma companies like AstraZeneca and with other, nowadays more moving into the healthcare sector. We have some use cases on this also. The cultural heritage is quite active also. We have interesting projects with both the British Museum in UK and Getty Trust out of LA. And down there at the bottom you see plenty of public and government institutions that are successfully using our technology.
Throughout the presentation, Atanas, we'll talk about a number of different terms, triple stores, RDF databases, and typically we'll use graph database. Can you distinguish graph databases from RDF databases, and then tell us specifically how are RDF databases really different in the market today?
Yeah, to start off with the graph databases, that's quite a broad term that shows like an umbrella for plenty of different technologies. But yeah, clearly all these databases use graphs as a data model, and by design and by nature they are schema agnostic, unlike, for instance, relational tables. And yeah, generally speaking, graph is one of the very expressive and powerful models that you can use. That is more powerful, for instance, and more expressive than trees, underlying XML and XML databases. So that's pretty much everything that you can say about graph databases if you take all of them together. And triple stores are quite a specific type of graph databases. One of the most distinguishing features is their standard compliance. So they use RDF as a data representation model, RDFS and OWL as a schema modeling ontology modeling languages, and Sparkle as a query language. What is also very distinguishing between them and other graph databases and NoSQL databases is the query language, Sparkle. Essentially, Sparkle is as complex and as comprehensive as SQL, and this allows you to get quite complex tasks done just writing a declarative query. That's not the case with engines like Mongo and other document stores. Neither is the case with key value stores. These are all technologies that are more designed and geared towards simpler retrieval queries. And the major difference with graph databases that use Gremlin and Cypher, those of you that know Gremlin and Cypher, they are more like script languages that allow you to get very specific jobs done in terms of graph analysis and traversal. But the weak point there is that they're very sensitive to schema changes and changing in data patterns, because these scripts would no longer work once you change the data, while SPARQL queries are more abstract and more declarative. So in plenty of ways, triple stores combine the beauties of both NoSQL and SQL. So their schema are the way in which NoSQL is, but they are most of the engines, particularly GravityBe, they are ACID, so they care about consistency, and they can have consistent behavior when this is what the application requires. It's going to be a long list, but two more things to mention is you're all aware of this linked open data movement and the fact that there is a rapidly growing amount of data sets getting public. And this is precisely what RDF is designed for, so that the best language to deal with multiple data sets across different servers, to merge data, and to use them without clashes. The last thing to mention, and we'll spend more time later on today with it, is inference. So triple stores are designed to support inference and to allow the engine to interpret the data that helps in various ways.
Speaking of that, a lot of the people who dialed into the webinar saw an invitation that had a simple representation in a visual form of a graph database, and I realized that with tens of billions of RDF statements, they can get fairly complicated. But in this simple visualization, can you point out some of the unique aspects focusing on RDF statements that are explicit in the database, inferred statements, and some of the data sources that have been used to create a graph like this?
Yeah, a simple example is if you see this chain of control that goes from Big Bricks Cafe to Global Investment Inc. down to my local cafe. So in a triple store that supports how you can declare that controls is a transitive relationship. So the triple store will infer for you that Big Bricks Cafe actually controls my local cafe. And then another demonstration here that you can easily merge company data like this control relationships with the geographic data that you see in blue here. All this information that's yellow is part of Washington, that's part of USA, and that West Bay Alpha facility is part of the Cayman Island that happens to be an offshore zone, and New York is also part of USA. So you can see inference with all these dashed arrows that allows us to infer that, well, actually Big Bricks Cafe is located in USA, and Global Investment Inc. is actually located in Cayman Islands, and my local cafe is also in New York. And here's where you can immediately take benefit, because with some quite simple definition, you can unveil suspicious relationships. Like in this case, you have U.S. company that through an offshore company controls another U.S. company, and this way you can infer suspicious relationship that an application or an analyst can look at and use.
So to construct something like that, you've used a number of different databases, but they've all been stored inside of the graph database. So it sounds like the data integration side of a graph database is a nice thing. But what does it really take to make this work? What kind of code is involved in developing that suspicious relationship that you showed on the left side of the graph?
Yeah, you can do it in plenty of ways, but it's not massive work made in terms of data integration, made in terms of defining views or queries, because you need to have a database of locations. You can get a free one like geonames. You need a database of companies. You can get a free one from Open Corporate. You can buy one from one of the many vendors. And then all the semantics that you're actually using in this example is transitivity of relationships like subregion and controlling relationships between companies and a simple rule telling you that located in is transitive across subregion. And then to define these type of suspicious relationships that your application may be interested in is as simple as this construct query. That's a simple SPARQL query. So it's good for coursework for students.
Okay, so let's transition now and compare RDF graph databases to relational databases. This is a little bit more complicated example, but it is showing existing data that you have, property classes, subclasses, RDF types. Tell us a little bit about this, and then let's talk about how it compares to a database schema in a relational world.
So the one thing that you can see in this diagram is that you see in yellow some very concrete facts like Ivan is child of Maria. Also, you see schema definition like woman is subclass of person, subclass of agent, along with some properties like child of and parent of and relative of with the relevant semantics. And you can also see representing the very same model some meta properties and meta schema at defining our symmetric property and our inverse of. So that's just demonstration of the entire approach that RDF databases are taking of putting all sorts of information in a uniform graph representation.
And when we compare that to a relational database, what are some of the advantages? And let's talk a little bit about the composition of RDF statements in the form of subject, predicate, and object.
So you can represent a graph like the one that we just seen in a table with three columns. Like the subject is the node that you're starting of, the predicate is the type of the relationship, and object is the end node. So clearly in this table we can present everything. In fact, triplestores does not use precisely these kind of tables. Inside there have been plenty of attempts to use relational technology with this kind of naive tables to do it. It doesn't work, but that's a good abstraction. So about the way information is represented inside a triplestore. And if you have to do the similar thing in a relational database, you have one table per class, per type of object, like person, and then one table for each of the relationships. And there are pros and cons of both approaches. I'll mention just two. So in SQL, having this structure that you see on the left, you have no easy way of asking for a relationship of unknown type. It's just that select doesn't allow you to do this. You should say from which table and which column you're trying to address. Well, and in RDF, it's one of the most natural things to ask for a triple pattern with the predicate as a wildcard. So that's the one advantage, searching for relationships of unknown types. And the other one is what I call schema agility. So the representation of data in triplestores is agnostic to the schema. The physical representation does not follow the logical schema. While in relational database, if you have a big database with like plenty of information about people, adding a new column to the specific table or changing the format of a column can be quite an expensive task. So the triplestores are much less sensitive, and the overhead and the penalties for schema changes are much smaller.
You've had a lot of experience deploying RDF graph databases. I know it's a little difficult to boil it down to sort of 4 themes on where they're most useful, but what is RDF really good for, and where would you focus?
On the one hand, it's about intelligent mapping of queries to data. So these methods to work when an application should query data set combined from, say, 10 or more sources, each of which depending the evolving on its own. There is just no way in which an application developer can stay on top of all the schemas of these sources and data sets all the time. So with information coming from multiple places, most of the standard approaches just doesn't work. You need to have some very efficient way to align schemata and to ask queries that are abstracted and more general than each of the specific sources schema assumes. What is more AI style, more intelligent feature is finding patterns and inferring new relationships. So think of someone who's constantly looking at patterns that elicit new relationships, which can match patterns that elicit other new relationships, and so on and so forth. So it's yes, having a detective or an analyst who's searching for these patterns over and over again and building on top of one another to find, to unview hidden relationships that could be unveiled with following this this type of patterns. And this is what reasoning gives you for free. So you don't need a person to do this. You just tell these simple things to define this semantic schema level, and it's interpreting the data for you. So this way, the final result is that when it comes to data integration, you get much lower cost of data integration and querying data coming from multiple sources. And you also get in much deeper experience and more complete results because of the fact that doesn't matter how many steps it takes for one company to control another. The Inference did the job to make this to follow these chains and to make this available query time. So yeah, these are the major benefits.
Okay, let's talk in a little bit more depth about your second point. I certainly like the fact that you can develop implied inferred statements, and that helps you discover information a lot faster. But you said you're able to link text and structured information, and that there's so much unstructured data out there. How does that work with a graph database and specifically GravityBe?
Yeah, one of the good applications so far the database is about content management, and that's precisely this capability of interlinking text and data. So we have defined, we use the term semantic annotation, and we mean that whenever you do this, you use information that's available in the semantic repository to analyze the text, and whenever you encounter something in the text, you expand the database. So this way you can benefit in both directions, and you can interlink the text with reference to the database. And graph database, particularly triplestores, are particularly suitable to do this because text analysis, if you do anything non-trivial, does require a lot of context about each of these entities that you're working with, or each of these concepts, to be able to disintegrate between Paris in France and the person Paris Hilton.
So a little later, we'll talk about the ability to go ahead and query NoSQL databases and the graph database at the same time. So that's an interesting idea and capability that I'd like to explore in a little bit more depth. But let's transition now and talk about inference and reasoning. So why is inference really important, and what does it mean for businesses that are on the phone today?
Well, I believe we covered most of this already. So it's all about abstracting queries from data and lowering the cost of data integration and finding patterns in across big data sets, providing complete answers. And it's also the case that through inference, you can get faster query evaluation. So you can see one of the approaches for inference that is materialization as a special kind of indexing that allows you to write simple queries which are also faster to evaluate.
Okay, so what I'm hearing is that inference provides you with a number of things. We talked about query flexibility, the speed of queries is improved, data integration costs are reduced as part of that, and it also sounds like users can ask general questions and get very, very specific, accurate results. Tell us a little bit more about that and how lightweight inference works.
Well, yeah, using this sample graph that we have just seen. So imagine that in one of the data sources that you deal with, there is this fact so that Ivan is child of Maria. And now imagine that in a query, in an application that doesn't know about this particular source, its specific format, you have a query asking for this pattern. Try to find Maria relative of X. And the short story is that through reasoning, you can get this query processed such a way that Ivan is returned back as a match for X. And that's precisely this type of abstraction of the query from the concrete format and the concrete syntax and vocabulary to assert data. That's this simple type of intelligence that allows you to get a relationship. Doesn't matter that it is a more specific one is mentioned in the data and it goes in the opposite direction, and you can still get it.
So what reasoning strategy are you using to accomplish that? Is that forward chaining, backward chaining, and give us a little bit more depth on that, please.
Yeah, one simple way to deal with this is through forward chaining. So all the semantics that you need to deal with this example is encoded in the 5 rules that you see on the left-hand side. And these are rules like you have in many languages, in many paradigms. For instance, if it's about defining the semantics of subclass relationship, it's telling you that if you have a chain going from C1 to C2 and then to C3, you can infer that C1 is subclass of C3. And then other rules similar to this one, that's everything that you need, essentially matching the first part of this rule, and whenever you get a match, you can infer what is in the head of the rule, that is the second part of consequence. And that's not a new thing. Essentially, this type of logical formalism, it is a simplified version of data log that's known in the database community since the 80s.
Okay, so you mentioned forward chaining and backward chaining. So what are the advantages of each one? And for anyone who's dialed in today, what would you recommend they use?
Well, for forward chaining is precisely what we just saw in the example. So you start off with data, with the graph, and you apply rules to infer everything that could be inferred. And this result, this process is called materialization because you materialize implicit facts. And this entire amount of data that you can infer is called inferred closure. And backward chaining is a different story. It's like whenever you get a query or a specific data pattern that you are interested in, you start applying the rules in the reverse direction to expand the pattern. I can probably provide some examples to this.
All right. So it sounds to me like what ends up happening with inferencing is number one, you're creating more inferred facts. Of course, then queries become faster and data integration is a little bit easier. But I would also imagine that managing the database can become a little bit different. In other words, if you're creating a lot of RDF statements and you delete an explicit statement that's been used to infer new statements, how do you manage that?
Yeah, just to come back to your previous question. So the major thing about forward chaining and backward chaining is that forward chaining takes time and effort when data is loaded or when data is updated, while backward chaining takes time when queries are evaluated, essentially. Yeah, we don't have the time to go deep in this in the technical sense. But backward chaining, there are 2 or 3 different ways to implement backward chaining, either by unfolding patterns or by query rewriting. But once you have big volumes of data, that's very, very inefficient. So whenever you have big scale of data, your only option is forward chaining. But yeah, to the question that you asked, what happens when you delete a fact and when the engine should make so that this inferred closure is correct. And that's a well-known issue with all reasoners and triple stores that use forward chaining. In the past, what you had to do was essentially to reinfer everything from scratch each time when there is something deleted, and that's still the way most of the engines work. Specific feature in GravityBe is that upon deletion, we have an efficient algorithm that allows us to figure out which are these statements that are no longer supported and that should be retracted from the inferred quotient. And that's about as efficient as adding statements and inferring new facts, which means it's efficient, and I mean, you basically don't need to take any of offline operations to a database. You can do it in a transactional fashion. And the final story on this is that you have efficient inference support all the way from loading data and updating data and deleting data through query support through the entire life cycle of the data. You inference essentially works transparently, and that the developer, the DBA, doesn't need to care about it. And that's the best of both worlds. Speaking of forward chaining and backward chaining, that's precisely the type of setup that you need to be able to handle like scenarios where you have plenty of updates. What happens, for instance, in media, and then you have to also to handle large amounts of read queries in parallel.
Let's transition and talk about some of the other essential features of graph databases that you think are significant, including geospatial indexing and the integration with full-text search and NoSQL engines. As you talk about these, can you give some business use cases on where they would be relevant, Atanas?
Yeah, okay, so there are a few things that you essentially can't do efficiently with triples and just with the normal indices that triple stores have. Now, handling geospatial constraints is one of them. So if you, similar to other databases, including relational databases, if you need to do queries that address specific geographical regions, or where you have constraints, like I'm interested in airports that are within 100 miles of specific city, to be able to handle this efficiently, you need special type of geospatial indices. And a few of the triple stores have those, including GravityBe. Then whenever you're exploring data sets that you're not so familiar with, again, these data warehouses of data combined from multiple sources, it's very, very valuable to have some sort of ranking of graph nodes or statements, clusters in the graph, so that you can to make it easier to figure out which are the more important pieces of the graph and which are less important pieces of the graph. That's again something that doesn't come out of the box just by the fact that you have indices about triples. GravityBe has a special plugin along with many other plugins that allows you to rank graph nodes and to order query results, for instance, by the importance or centrality of the graph nodes. The last two features mentioned here are, well, our CMS is a feature that's very, very useful when it comes to data integration, but you need specific support for it to do this efficiently. The same applies whenever you want to have a decent integration between standard Sparkle query with all the triples and filters in it, and full text search query that is just a full text search query.
So if somebody's creating RDF statements and they're doing that from free-flowing text, and we identify that an entity is basically the same but referred to differently across documents, is that where OWL same as optimization is applied?
Yeah, that's one of the cases, Tony. Precisely. You can get multiple, whenever you analyze text or you combine data from multiple sources, you need to do the so-called reconciliation or entity identity resolution. But to give you a simple example, imagine that you're bringing together DBpedia that has plenty of information about everything and geonames that is about geography. Sorry that this example is a little bit cryptic, but you can think of the statement that is saying, well, New York City is part of United States of America. And then think think about what's going to happen if you have several different identifiers about New York City and several different identifiers about United States. So to be able to query the data using the different identifiers and get identical results, you can connect those with these, in this case, like green arrows connecting the different alternatives. But if you have to apply the brute force inference to infer all the variants of these statements that you should be able to query for, you can easily get a single statement expanded by 6 times, 10 times, or 20 times. That is unpractical. It's good that you can see query data using different vocabularies, but this price of expanding indices and also query results multiple times is not a good one. So to make this practically usable, we have implemented optimization that gives you all the benefits of Alzheimer's reasoning without these performance penalties and expansion of query results. And this works entirely transparently in the engine. You don't have to care about it.
I would imagine with the growth of those SQL databases and content stores that the need to go and query both the documents and the graph database at the same time is very important. Tell us a little bit about the definition of GravityBe connectors, and then let's talk about how they work.
Yeah, I already mentioned that we have a plugin architecture that allows us to essentially combine the core engine with its standard triple store indices with various different modes of indexing and querying. And we have used this architecture to implement integration to full-text search engines as well as to NoSQL databases. And yeah, I mean, full-text search engines are way better when it comes to tasks like faceted search or incremental search, whatever. Just because their indices are constructed in such a way to make this well. They denormalize the data, they are inefficient for other tasks, but there are some things that these engines do quite well. And the best way to deal with this is to essentially provide integration that is as smooth and easy to use as possible. That's what we did, both for the information retrieval engines and for NoSQL databases.
And how does this all work? How are the indexes connected, and how's the query processing operating?
One scenario that is particularly suitable when it comes to integration with engines like Lucene or Solr or Elasticsearch is a pattern where updates are always going to the triple store, like you see them with blue arrows here, and the triple store takes care to update. To generate the relevant documents that are passed, that are indexed by the full-text search engine, and to keep those in sync with whatever we have in the triple store as data. And then query time, I have a choice. Queries, read queries are depicted here with red. So query time, you can either directly send queries to the full-text engine, either which is more powerful, go through this, or the triple store, make a query that combines structured query with full-text search pattern.
Okay. Let's go ahead and switch over to enterprise resilience. It seems like more and more businesses have to have all of this running uptime 99.9%. So tell us a little bit about graph databases and why and how they're enterprise resilient.
Well, we have a cluster architecture that's designed for two purposes. The most important thing was to guarantee resilience, so to make sure that there is no single point of failure, and the other thing is to make sure that we can process really large amounts of queries, because we've seen quite a lot with many of our clients. You should be able to handle if you are. For instance, if this is the engine that's behind the website of PDC, at some point you can face millions of queries per hour. and you need to be able to scale to handle this load.
Very good. And does that exist inside of a replication cluster? How does the replication cluster really work?
Yeah, that's the architecture that we got up and running like 4 or 5 years ago. That's a replication cluster where you have some master nodes that control the entire story, and worker nodes that are actually standalone triple stores. So whenever update comes to the cluster, it's dispatched to all the worker nodes, while read queries are load balanced and dispatched to different workers. So that's the core mechanism. And you don't have a single point of failure because you can have multiple masters, and clearly you have multiple worker nodes, so that there is no situation in which one of them fails. You get your cluster non-operational.
Are there limitations? Can this run across continents? How many master and worker nodes can you really have?
Yeah, we've been running this architecture for like 4 years. That's precisely the setup and the technology that was running the website of BBC and then the websites of many of the biggest publishers in media. But this year we decided to develop a second generation of this architecture that is mostly about being more efficient about the ways in which the cluster recover in case of whatever problems with the worker nodes, making sure that it works efficiently whenever you have cluster distributed across geographically remote data centers. Think of having one data center in London, another data center on the East Coast in the US, and another in somewhere in Japan. So to support this efficiently, you need to do quite a number of specific things to the cluster architecture, so that whenever one data center is down or inaccessible, you can very easily recover after this situation and put all the data centers in sync, for instance. So that's the second generation of the GravityBe cluster supports all these scenarios. And to give you a feeling of what it takes to get there, the core functionality of all these resilience algorithms was implemented, say, in 3 or 4 months by part of our team. And then it took 6 months to make sure that all acceptance and stress tests are passing, testing all the hypotheses of different failures. So knowing the competition, you don't have that many mature enterprise cluster implementations for triple stores.
You know, over the 15 years, it sounds like you've built a tremendous stack of technology. One of the things that I find most fascinating is the integration with text mining pipeline. And this simple graph shows, a typical text mining process. You can talk specifically about that briefly, but I'm most interested in is once the RDF statements are created, the classification and disambiguation has taken place. What happens in the semantic indexing side of things? Are ontologies, taxonomies, RDF statements all bound into GravityBe?
Yeah, the entire process goes like typically goes like some rudimentary tasks in natural language processing, all the way from optimization, sentence splitting, purpose speech tagging, and similar things. And then the next step is that you basically use this integration between the triple store and the text mining components, because you can fetch entity names and other information about entities out of the triple store and look up these entities in the text. Then usually there is a set of statistical based methods where we do classification or reclassification of all these entities, and the most important thing is disambiguation. Again, this story of being able to distinguish a string in the text that is speaking as Paris, being able to put a link to the proper thing, not to mix up Paris in Texas with Paris in France or Paris Hilton. Whenever you have to do more complicated text analysis jobs, like to discover relationships between objects or entire events, you usually use grammar-based parsers, then use rules. And that's pretty much it. At this step, you're usually done with the task. You have encountered all the entities and extracted all the facts that you wanted to, and you get to the semantic indexing step, and that's what you've been asking for. If I have to simplify it a little bit, it's just about putting together your ontologies, your taxonomies, all the relevant data sets, your databases, to store them in the same triple store together with the metadata that is telling you which of these entities are mentioned in which of these documents. And to have all these also connectors to allow you to, for instance, whenever it is a search scenario, to efficiently make searches like, give me documents that are speaking of managers of telecoms in US. It's a combination of structured query that goes to a database and takes all the managers of telecoms in United States, and then searches for them in the full text indices. So to make this work together and to be able to put these two words together, that's what we call hybrid indexing and hybrid semantic indexing, that allows you to take benefit of both structured queries and inference and the typical beauties of the full text search.
As you go out and market and sell this technology, it sounds like to make it work, you've developed a lot of integrated pieces that are part of it. I know you've got different versions of GravityBe, Light, Standard, and Enterprise, but tell us a little bit more about the platform itself and then the kinds of solutions that you've built for customers.
The platform is precisely all this technology that you need to implement this tech that you've seen on the previous slide, all the way from text analysis to semantic indexing and to get this delivered in an application. So semantic enrichment is this part that involves text mining, but usually before you can do that, you have to integrate structured data that you can get from different sources to do a lot of so-called ETL, extraction, transformation, and loading, or to acquire content through web mining. So these are all different tools that we use in different applications, and that allow you to build this tech. Another thing that you always use whenever you have text mining and data integration is you need a lot of curation tools that allow you to develop gold standards and to evaluate accuracy and precision so that you know how clever and how good your clever extraction algorithms are. So we have more than 5 or 6 different curation tools internally that are good for different jobs. So that's a big backup technology that allows efficient implementation of such applications. The concrete application that we have shaped so far, one of them, and probably the most popular one, is a solution in the media and publishing sector. That's about everyone who's in content delivery. Then a vertical that we pay specific attention to is life science and healthcare and biotechnology, because you have to deal with specific data sets to be able to comprehend their semantics, and you also need a different parser and tagger that can identify these kind of entities in text. So the typical parsing techniques that are good enough to extract people, persons, locations, and organization out of text are not the same that you need for proteins and protein interactions. And the last thing that you see on the right-hand side is more a tool oriented for enterprise document management with typical applications in compliance. So that's the current technology portfolio.
So one of the topics that we haven't touched on in great depth today is a question that just came in. It sounds like there's a lot going on with graph databases. You're loading RDF statements. you are querying them at the same time, delivering results to websites and other applications. And in some cases, you're doing inference there. Can you, as we kind of go through the case studies, can you speak a little bit to some of those issues? What have the challenges been and how have you overcome them?
Yeah, speaking of the concrete scenario of BBC, that's probably the most popular application of semantic technology ever. The first application of the dynamic semantic publishing paradigm. So the scenario is a news article comes to the BBC. It is being processed by our semantic enrichment pipeline so that we generate, say, 20 or 30 or 50 concepts and entities that are most informative and most descriptive about this piece, and it goes to an editor to curate this metadata, and then it is stored in a triple store. So what they use this metadata for is to dynamically generate web pages. So whenever someone asks for the web page for Frank Lampard on BBC's website, this page is being generated from a template by means of several Sparkle queries. So that's a scenario where you have plenty of updates, like whenever you have a big sport event like the World Cup or the same technology was used for the Olympics, you're getting at some point millions or tens of millions of queries. And at the same time, you have a massive flow of new content that is being annotated, processed, and that should be stored in the triple store, so that in the next second it is available and can pop up on the website. So the major challenge here is how you combine these two requirements, providing a consistent database with very low reaction times and very high transaction rates, combined with inference. And we've been able to do this using this forward chaining approach, including the retraction mechanism that allows the people at BBC to, whenever necessary, to delete stuff and to keep the entire system operational.
Okay. Is there any other point you wanted to make there, Atanas?
No, that's fine. We should better leave some time for questions. So I'll tell the story about this application with AstraZeneca, and we can spare some time for questions.
Yeah, I wanted to talk a little bit about AstraZeneca as a search and discovery app, and I do want to touch on the cloud-hosted version of this at LMI quickly. It sounds like people are, with massive amounts of documents, it's hard to find, and a lot of times this can speed up the entire search process. So let's talk about those two applications, and then we'll wrap up.
Okay, so in AstraZeneca, as any other pharmaceutical companies, they are by law obliged to answer inquiries from agencies like the Food and Drug Administration Agency, the Food and Drug Agency. So they're asking questions about any clues about side effects of drugs. And they should answer these questions in a very comprehensive manner. So they're not allowed to miss any possible evidence. So to do this, we build a system for them that combines multiple databases, like this impact database, MLCS, AstraZeneca with data about biomarkers and other things, in a single data set within GravityBe. Then we have to process a big amount of documents, for instance, clinical trial reports for drugs, so that we can annotate these clinical trial reports with references to the database. And the final application is just a better, more efficient search. So whenever such inquiry comes, the people at AstraZeneca should be able to provide complete answer in very quickly. This system is running in production for more than 2 years now. We managed to reduce the query answering time more than 5, the inquiry handling time more than 5 times. And in this case, text mining is particularly demanding. If you can just switch to the next slide, because you should do good sectioning of the text. And if there is an inquiry about, for instance, some issues between soundtrack and asthma, whenever you find asthma in the text, you should know whether you have found it in the header of the document, or you have found it in a table that is speaking of adverse events. That's the context in this case is extremely important. So that's a very comprehensive system. Let's go to LMI, and then we can wrap up.
Yeah, I have one question I'd like to ask you, though. We talked a little bit about Solr earlier and integration with Solr. What impact does this have on the index size as we integrate with Solr, and does it support the Solr cloud at this point, or is that something that you have planned in the future?
Well, in this case, indeed, the system works through integration with Solr with this connectors feature, and yeah, the integration with Solr is actually reducing the size of the indices, the main indices of the triple store, because yeah, you can offload to Solr all the denormalization that should take place in order to support good faceted search and co-occurrence queries and these kind of things. So yeah, we do use Solr and actually distributed Solr setup. Yeah, I mean, for Solr, dealing with big volumes of data and denormalized data is not such an issue, because this is what this engine is built for. So they have the relevant compression techniques and update techniques that make it efficient to work with these volumes of data.
Okay, great. And let's start to wrap up. I want you to talk about LMI and specifically open policy, which you built in conjunction with LMI. What does it do, and what should people remember about open policy?
That's an application that we developed together with the Logistics Management Institute out of Washington, D.C. That's a non-governmental organization that works with most of the agencies in the U.S. government. Then they spotted a problem across all of them, that sometimes you're getting such massive amounts of regulations that searching through them and finding the relevant pieces is a big pain. So think of a concrete scenario where maybe one of the installations is in the Department of Defense. So think of maybe officer that's trying to figure out what are all the relevant regulations when he's trying to transport, to ship a military truck out of a military base in South Korea to Germany. So essentially, quite a lot of the information that he's searching for is hidden within PDFs that are 700 pages each, that come in multiple versions that amend one another, and you have hundreds and thousands of those. So we have implemented a system that does more or less the same thing that we discussed so far. So integrate relevant taxonomies, databases, vocabularies, dictionaries in a triple store, so that we can efficiently analyze these big volumes of text. And again, in this case, sectioning is quite important, because we weren't allowed to return back a PDF of 700 pages. The entire system works so that it gives you back very specific pieces of these documents that are relevant.
Very nice. We're going to skip to Euromoney, but if folks want to find out a little bit more about it, they certainly are free to contact us. For the sake of time, though, we'll wrap up here. These are the essentials that you've listed here. Are there any topics that you'd like to just hit on one more time? Things like full SPARQL 1.1 support and things you've done there, or you feel like you've pretty much covered these topics, Atanas?
Well, yeah, again, that's like mentioning which are the features that we found fairly important and beneficial to our clients, and that one should consider. Like, there are really very few triple stores that are as mature as to have proper cluster architecture with all the resilience features that are required for live operation of someone like BDC's website. The other important thing is inference. So I mean, a major reason for many people to use triple stores at all is that they need inference to help them with data integration or with finding patterns in data. It is very important to make sure that you have an implementation that is efficient across the entire life cycle. So it doesn't matter whether you load the data or update the query, it works transparently. And the major choice is again between forward chaining and backward chaining. For any decent size of data and for any queries, you even don't need complicated queries. Backward chaining can get too slow. So essentially, that's one of the reasons that we found. So we have standard compliant support for RDFS and for OWL in various flavors. And we found out that this combination of forward chaining and smart retraction techniques is the one that delivers. Sparkle 1.1 support. Well, I would suggest anyone who is choosing a triple store to get it validated through public compliance data sets, because it sounds easy and it sounds like the difference between 1.1 and 1.10 is small, but it's not. It's a very, very massive step actually. That's not particularly good that they just labeled it 1.1. Doesn't matter. So it's a big thing, and you care about it. GravityBe is entirely implemented in Java, so there are no portability issues across platforms. And altogether it's built on top of the Sesame open source architecture. We also have the compliance with Java, but Sesame is in the core of the engine, and we are also the biggest contributor to the Sesame platform.
Atanas, I'd like to thank you for putting up with all my questions over the last hour. I know there are additional resources out on Ontotext.com, including white papers and GraphDB summary sheets and benchmarks, but I do have one more question for you. As a prelude to our next webinar, which is on S4, the Self-Service Semantic Suite, I know you just released S4 that runs in the Amazon cloud. Can you tell us just a couple of quick things about S4 and why developers would really care?
And the major point is to be able to experiment and to build the prototypes and proof of concepts without being bothered with the installation, configuration, setup cost, and finding servers and everything. So there's a typical story with any cloud infrastructure. It's just that we made both the database engine and the text mining pipelines and everything between them available to Amazon Web Services. So one can very, very easily set up an application type technology without any complications.
Yeah, I used the free demo that was out there at s4.ontotext.com, so it works well. Even I could use it. I'd like to thank everybody for attending today. Not all graph databases are created equal. Thanks for taking the time on a busy day. Atanas, thank you for your time. A link to the recording that you can share with your colleagues will come out very soon. And if you have additional questions, you can always send those to info@ontotext.com. Thanks for your time today.